Welcome back. Today we're going to start learning about finite state machines. Finite state machines are an approach to solving more complex problems. So this is a skill that you're definitely going to need for the PLC lab because we're going to require you to use it, right? But it's also a skill that you might use for your project as well. Really, it's just a systematic way to approach something, and then there are ways you can implement that plan in your code. So let's just go ahead and take a look at a finite state machine. A finite state machine is pretty simple. You have circles, which show states, and then you have arrows, which show transitions, right? So here we've got a basic turnstile, like you might find at the SRC or something like that. This one is coin operated. So it essentially has two states. It might be locked or it might be unlocked. If you are in the lock state and you put a coin in, then it becomes unlocked. If a person pushes through it, then it becomes locked again. So those are the states. If you're sitting in the lock state and somebody tries to push on you, it will just stay locked. And if you're unlocked and people put in extra coins for no apparent reason, you just stay unlocked. Then the last thing is each finite state machine needs to know a place to start. This little line here is the reset. So when the system turns on, you go here. Finite state machines have been around for a long time. People use them not only to express like the ideas, but they also put in details so that they can implement them better. The main detail that gets added for implementation is that in each state, people put a bar. Above the bar, they just put a name for the state, like you saw in the last slide. And then below the bar are where the actions are going to go. And the actions are important because it helps you understand what should be going on. It also is important when you implement it. The last thing that gets added is that states typically get a number. It depends on what system you're going to implement it on, what type of number you give it. But it's a way to not only identify it, but also like when you get to the implementation to help you make this thing happen. So here you can see there's, a simple little 2-number system for a door opening and closing. So let's go ahead and get some practice with these guys. So what we've got is we've got a finite state machine. This one is complete. So you can look at this finite state machine and kind of see what it does. So this is obviously for a door opening and closing, right? So the door starts off open. That's just kind of, we're pretending, our pretend system, that's how it starts. It assumes the door is open by default. There are 4 inputs. There is a command to open and close, and then there's a sensor that says when it is actually opened and when it is actually closed. So for example, if you press a command to close, it will begin closing. Here I gave closing the output Q2 because that's what a PLC might need. And it'll stay in the closing state until that sensor comes along and says, hey, I'm now closed. Then it'll be closed. If the door was used logically, the next thing somebody would do is they would press the open command. It would start opening. And then when the sensor says it was completely opening, you would get back around to the start. So what I want you to do is in your notes on the next slide, there is a timing chart with a bunch of inputs for those 4 inputs. And then there's a little reference to the finite state machine. See if you can go through and complete Q1 and Q2 all the way across. I'll give you a hint. Sometimes it's nice to think about what state you're in. So like, even though we haven't shown it to you on the timing chart, maybe like you could just jot down like what state number you're in. They're actually numbered 1, 2, 3, 4, kind of clockwise around. All right, take a minute and see if you can get that together. All right, I'm going to go ahead and do the solution as well. I'll just pop it in, then I'll talk about it. All right, so I just went ahead and popped it in real quick here. So what this kind of is going through is I'll just kind of talk about the first part. So first off, somebody says, hey, close the door. And so no surprise, Q2, which is the door closing, it comes on for that interval. And then as soon as the door is shut, it turns off, right? Likewise, if somebody says open the door and then the door opens, you've got the motor that was actually turning it on open for that interval. I found that the easiest way to do this was just to go through and just figure up the states all the way across first. So that's what my numbers are on the bottom here. So I just wrote down what state I was in to help make this thing faster. Here you've got the situation where one guy says open, and it starts opening, but then somebody else says, somebody says close, then they say open, then they say close again, and the door the motor just goes back and forth based on what you wanted. Here it actually became closed. This situation is a very impatient person hitting open, 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 open. You can see it does not affect the motor. The motor continues to just try to open until it gets there. And then the rest of it is just kind of some gibberish. So I threw on some things that shouldn't happen, right? So you shouldn't see a signal like that, but what would the finite state machine do with these signals? And so some other things just to see if you can handle it. Hopefully you're able to match up with my solution, and hopefully it all makes sense. All right, so that's kind of one skill, is reading a finite state machine. We typically evaluate whether you can read a finite state machine with timing charts. It's a good way to do it. Let's see if you can build a finite state machine from a problem statement. So the problem statement here is a dog. So this is a rather simple dog. It barks, sleeps, and sits on the couch. So there's three things it can do. So you've probably got a good idea for how many circles there are going to be. The inputs on this are whether the sun is up or not. So if the sun is up, that means he's not sleeping. If he's hears a noise, he's going to start barking. This particular dog barks for 5 minutes. Whenever he hears a noise, doesn't matter if he's asleep or awake. If he hears a noise, he's going to start barking. Just to make sure you've got it, let's just go ahead and do a quick timing chart together. This one I'll just do with you because the goal is for you to build the finite state machine, not the timing chart. So he starts off, he should be asleep, is how I want you to start this thing off. And so that tells you where the reset arrow should go to. If he's asleep, where the reset arrow should be, and there's no sun up, he's snoring, right? And so then, obviously he's not going to be snoring for that interval. If he hears something, so here he heard a noise, what you should do is you should start barking at that spot. He's going to bark for a total of 5. And then in this part right here, he's done barking. The sun's up, so he must be on the couch, right? So make sure your finite state machine catches that. Here he hears another noise, so he barks for 5. Notice that the sun went down while he was barking, but that doesn't affect barking, right? He keeps barking until he gets his 5 for barking in. But here he's done barking, and the sun is down, so he immediately goes to sleep, which admittedly is a little unrealistic, but that's fine. And then he hears a noise from his sleep, from his slumber, and that's fine. He wakes right up, starts barking at the noise. So that's what your finite state machine should look like, your timing chart of your finite state machine should look like. I just wanted to do this first. To be honest, it's harder to do a timing chart without a finite state machine, but I wanted to test you on the creation of the finite state machine, so we did the timing chart first. All right, so there's the timing chart. Now what I want you to do is draw me the finite state machine. Make sure you put on all the arrows for the transitions. Make sure you also put that reset line in and which state it's going to go to. So take a minute and see if you can draw a finite state machine. All right, I'm going to do it as well. So we can see that we had 3 states, right? So we'll just kind of start off with 3 states. We'll call one of them, sleeping, and one of them barking. You surely put them in different spots than me. I mean, that's a completely arbitrary choice. And then we'll call the other one just couch. While he's in the barking state, he is going to be barking. Eventually that will get a cue once we start implementing this, right? If he's sleeping, he's going to be snoring, so that's the output for if he's in the sleeping state. And if he's on the couch, that's the one and only time he's quiet. The other thing that we will put in here later, but we don't need it yet, is a number. These would be assigned like 1, 2, 3, something like that. I won't worry about it yet. We need a reset line, so when this thing turns on, it resets to here. Now we've got to start putting the transitions in. So one of the rules was if he ever hears a noise, so these are both, if he hears a noise, he starts barking, right? It continues barking until some timer goes off. So if I can write the word timer. So that's a 5-minute timer. When we build this thing later, we'll make it a 5-second timer, but it's a 5-minute timer for now. And now we've got to decide whether there are inputs and outputs there are. If he's on the couch and the sun goes down, you would express as the inverse of sun. The way you draw that is you just put a bar over the sun. So there is no sun. Bar comes from and or not gates. It's just how you do inverse. And then if the sun is up and you're asleep, then that makes you wake up. So hopefully, if you're able to put together the finite state machine, you could see how if you're doing the timing chart now, all these things would make sense, right? So if you're sleeping and you hear a noise, you go up to barking. After the timer goes off, you get back on the couch. Interestingly enough, that one situation where the sun was down and he started barking, he actually did go to the couch, but it was instantaneously, like he went to the couch, and then instantaneously there was no sun, and so he just shot through that state and went to somebody else. That's fine, that happens. It was just shot through the state. It was so fast, like it didn't even get picked up on the timing chart, right? Because it just went right through. I've got a cleaner version of this as well, so it should look like that. All right, so that's your introduction to finite state machines. Come back next time. We'll try to implement some of these guys. See you then.